Hello, everyone. Welcome back to my project, and today we're gonna do a presentation for finite element analysis of a hydraulic engine mount, including fluid-solid interaction, and this is our progress phase 2. So, let's go a little bit back about what we did last time. For our last presentation, we did an introduction about hydraulic engine mount, some operational principles of the hydraulic engine mount, some application in the project, and my personal idea. And today we're gonna keep flowing up with the methodology. So in the methodology chapter, we're gonna discuss about two fundamental theory for static FEA, which is the progress of our group at the moment and for static, and a little bit about the fundamental theory for the fluid solid interaction in finite element analysis. And that's we gonna do for the rest of the class in order to finish at the end of the class. And for the last chapter is going to be chapter 5, and we're going to do some modeling and simulation for the hydraulic engine mount. In that chapter, I'm going to start discuss about how I designed a hydraulic engine mount step by step from the start, from the beginning to the end, um, and what component from the hydraulic engine mount that I grab out to doing a static analysis for that, how I assign the hyperelastic material for the rubber part of the hydraulic engine mount, and I did a little bit of very fine calculation for that part by doing hand calculation, and we did it through Excel. And other than that, for a little off from this topic, I also discussed a little bit about uh, the process of the fluid solid interaction simulation that I'm not going to cover in the table of contents today because it's going to be my last part for the class for the end of the class, and that's where I stop at right now. So I'm going to go a little bit about the hydraulic engine mount. So as far as that we talked before, the hydraulic engine mount is a small part that connect the engine and the chassis together, and its main function is to isolate vibration, reduce noise, so that it's going to bring the comfort for the passengers driving in the vehicle. And you're going to have two main operation principle for the hydraulic engine mount. So um, it's going to work in the low frequency and large amplitude excitation, which means that it's in the idling. And the key component that play an important role in this is the inertia track, and it's going to work as a resistance for the fluid flow from the upper chamber to the lower chamber. And the other condition is the high frequency and small amplitude excitations, which is like a very high RPM. And the key component that working in this part is the decoupler. Like so, on that time, on this high frequency and small amplitude excitation, the decoupler gonna let the fluid bypass inertia and from the upper chamber to the lower chamber, and it plays its function as a resistance also to isolate vibration. Okay, so we're gonna keep going with the part that I will start today. That is chapter 4, methodology. For the methodology, firstly, we're gonna discuss about the fundamental theory for static FEA. And I just take an example from the book that we studied before to add up some good information about how we uh, planning to calculate the stress, the strain, and the relation between them from Hooke law, and from that we're gonna get spring stiffness, and finally we got the elastic behavior of the element with nodes from nodes I to node I plus 1, as you can see like the function from your right. So this is the component that have the length L, um, the width 1 is on the upper part and is a bigger one, and the width 2 is the smaller one, and is under the effect of the force P. And from that, all of that functions, and we connect it together, we gonna get all the element together, and we got the global stiffness equation kg, and we're gonna have the function as the below one stiffness matrix multiply displacement matrix, you're gonna get the load matrix, and this is the global one. For fundamental theory for uh, fluid solid interaction FEA, I'm sorry I forgot to change the word static to FSI. So for FSI, you're gonna take a look of the mathematical module. So for the solid response, um, we're gonna use the Lagrangian formulation for large displacement and large strain. Secondly, we're gonna discuss about the rubber spring and the rubber bellow in the hydraulic engine mount, because it is a rubber, so it is a hyperelastic material, and you have to use a hyperelastic model to represent for that material property. So in order to do that, you're gonna have some types of model that you can use, like Mooney-Ravelin. You're gonna have Argin, and depends on what order that you're gonna use. And all of these parameters, it depends on the experiment that you doing for that rubber, so that you're gonna have uh, the parameters that gonna fit to the function of the model that you're gonna use by using a least square method. From that to get all the parameters in a function, and from that parameters you're gonna fit with the function that represent for your hyperelastic material, and when it fit into it, and you can use that parameters to utilize and leverage it in ANSYS to set up your material property properly. And you're gonna have from the fluid, we're gonna model it using the full Navier-Stokes equations for incompressible flow in Lagrangian Eulerian ALE form. You're gonna have continuity equation and momentum equation as on your right side. And at the end of after modeling the solid part, after setup for the solid part, after setting up for the fluid part, you're gonna coupling all of them together. So the boundary conditions leverage to this fluid structure interfaces are as above. So the dF equal with the ds, which means that the fluid and solid displacement gonna equal to each other when the hydraulic engine mount vibrate when it moving. And also the stress of the fluid and the stress of the solid part is gonna have a relation to each other. And so let's go to chapter 5. We're gonna do some modeling and simulation for the HEM. So for this one, I will talking about modeling first and how I designed the hydraulic engine mount. So looking at straight to the sketch on your left side, you're gonna see um, a basic typical uh, hydraulic engine mount, you should have there's rubber spring on the top. You will have the inertia track. Gonna have upper chamber. You're gonna have decoupler, and you're gonna have the rubber bellow on the bottom. And outside of the hydraulic engine mount, you're gonna have the case, like I'll call it a cover case, to cover all of the parts inside it, and it's gonna connect to the chassis also. So first thing first, I designed a rubber cap, which is a small middle part that in a rubber in a that connect into the rubber spring also, and this one is gonna connect to the engine. So after that, I started to design the inertia track and the track cover. But so when you started to design the inertia track and track cover, we're gonna have to think of where should be the inlet for the fluid going through it from the upper chamber. So while designing inertia track and track cover, I have to figure it out uh, to design an inlet for the fluid to go through the track cover. Then it's gonna flow through the track cover straight to the inertia track. And after flowing from the inertia track for 350-degree, we gonna see right there is the inertia track. You're gonna have the small hole at the end of the 350-degree in the middle picture, and that is the outlet for the fluid to go to the lower chamber. And that's how I designed it. For the structure of the inertia track, the track cover, and the rubber bellow, it's going to be fit in the middle of the cover case, so that I have to design the structure of all of them have to fit in the cover case and lock to each other so that it's not going to move around. And for the pre-processing of the top component of the HEM for the simulation, I took out the rubber part on the top of hydraulic engine mount to start doing simulation. So for because it is a hyper-elastic material, so I choose to use the Archin first order function to describe the material property for the rubber part. So based on the pictures on the screen right now, you're gonna see uni uniaxial test data. We're gonna have biaxial test data and shear test data for the rubber part. And the three important things in the Archin first order module, that is the shear modulus, the material constant alpha, and the bulk modulus. But the bulk modulus is going to be described as a incompressibility parameters in ANSYS, and it is the reverse side of the bulk modulus, so don't worry about that. But remember, these three parameters are very important while defining your hyperelastic material property in ANSYS or any kind of simulation tool. Uh, After finish all the things about the material properties, I started to machine the top cap of the hydraulic engine mount. So this is a rubber spring part and the cap part. So look on the top right corner, you're gonna see the mesh quality for this structure, and it's not so good as I expect. So we can see there are some red and orange line on the outside of the structure, so it means that it's not so good. It's not a good mesh. It's not a very good mesh. And after that, I put a fixed support condition for the bottom of the structure and a 200 Newton force on the top of the cap. And this is our result post processing. So we're gonna have on the top left of the corner, we're gonna have the equivalent stress result, uh, which is showing that it's gonna be 0.097 MPa for this. And on the top right corner is gonna be a equivalent elastic strain result. And on the bottom side of the picture will be a total deform, deformation of the structure. After finish the simulation for this one, I start to do a verification by assuming the cap and the rubber spring as a structure same like the pictures that I show on the screen right now. And this is the dimensions of the cap and the bottom of the rubber spring and also the length of them. And after calculating, we see there is some different between the stress. So for the stress, this is 0.16 MPa is going to be different with the stress that we got from ANSYS. This is 0.097, mostly zero point 0.1 MPa. So that's how I did for the progress phase 2, and I'm going to talk in a little bit more about what I'm going to do next for the other process. So the other process of mine is going to start doing transient structural analysis for the hydraulic engine mount. So this is a dynamic module for that allow you to model in your structure that have the function of force by time or function of displacement by time that you're going to put on. So for me, the hydraulic engine mount is going to connect to the engine and it's going to be vibration so that we're going to have the function of the displacement of the top of the engine mount by time or force that affect to the top of the engine mount by time, but I will use the displacement function. And this is how I mesh my structure. And as far as you can see on the top right of the corner, showing that I'm having a very not a very good bad mesh is good, but it's around 70 to 80% good. And I put a some boundary condition on it, like a fixed support at the bottom of the mount, the place that we connect to the chassis, and on top of the mount I put a displacement function by time on it, but haven't started running it yet because my computer is not good enough to run. The other pre-processing part for the hydraulic engine mount is some part that inside the mount. So on the top right of the corner, you're gonna see the inertia track, and the top left of the screen, you're gonna see the track cover that is meshed, and this is the mesh quality of the structure. And on the bottom side, bottom right, you're gonna see the case cover. Now, showing that it having a good mesh right now, and I'm happy with that. And for the fluid pre-processing part, so this is the fluid part inside the hydraulic engine mount. So on top of the fluid, you're gonna see that is the fluid part in the upper chamber. You're gonna see there's a link between the upper chamber to the inertia track, and from the inertia track, you're gonna see the link to the lower chamber. That is how the fluid flow in the hydraulic engine mount. And for this case, we're gonna divide it, the hydraulic engine mount to two different working condition: low frequency, high, big amplitude, and high frequency, small amplitude. So in two different working condition, I'm thinking of design designing two different model. So in a low frequency condition, the inertia track gonna work and it's gonna neglect the decoupler. And that is the reason why I will cover the decoupler part. So just let the fluid go through the inertia track. For the high frequency condition, the decoupler is gonna work more effectively. And I will cover the inertia track and only let the fluid go through the decoupler. So on the bottom of this screen, you're gonna see the pictures of a lump mechanical model for the inertia, for the hydraulic engine mount. And usually we're gonna use lump mechanical model to do calculation for hydraulic engine mount. And you're gonna see the xt, which is the displacement function that was set on the top of the hydraulic engine mount, and that is where I'm gonna put a boundary condition for my structure also. You're gonna see the P1 by time is the fluid in the upper chamber, and the P2 by time is gonna be pressure of the fluid in the lower chamber. And the QIT on your left side, this is a flow rate of the fluid through the inertia track by time. And the QDT by time on your right side, that is the flow rate gonna go through the decoupler. And that is what I have for my presentation today. Um, so I'm gonna talk a little bit about my what I'm gonna what I'm gonna do next. Like you're gonna see on the right side of the screen is a planning to do. So you're gonna see on the top left corner is a transition structural, right? So you got geometry, you're gonna connect it to the fluid flow, and it's gonna connect all of geometry together. But the hard thing is you're gonna um, connect the setup for the transient structural. You're gonna couple in with the setup of the fluid flow in the fluid module for the system coupling module, so that you're gonna get the whole total solution of your simulation in the system coupling. So hopefully I can make it at the end of the class, and hopefully that's gonna be a very good project for me. Thank you for y'all for listening. And if you have any question, don't hesitate to put a comment below or just shoot me an email and I'll try my best to answer you any kind of questions that you have. If you need to me to explain to you more about hydraulic engine mount, I'm willing to do it. So thank you for your listening and have a great day.